Okay, I think we can start now. Um, yeah. Okay, so hi everyone. My name is Jay. I'm vice chair of HackQuest committee this year, and I'm a third year penultimate student in NTU studying computer science. Welcome to the first workshop on neural networks for this semester. So if you have any questions during the workshop, you can either use the raise hand feature or you can put your question in the chat, or if you like, you can email me the question or your query later as well. So this workshop is a neural networks, and since neural networks is a it's a very broad area, it has a lot of components, and it's hard to cover it in 2 hours. So I'll be trying my best to give you an overview of what neural networks are, the basic intuition behind them, and how do they work. All right. So the agenda for this workshop will be, firstly, we'll be getting an introduction of what exactly neural networks are and in which category of machine learning do they fall. Then we'll be exploring what is data and what are the types of data that are there and which are used in neural networks. Then we'll be moving on to the fundamental concept behind deep learning on neural networks, which is forward propagation. Then we'll move on to activation functions, which are equally important. And then finally, we'll move on to how do we actually train the neural network by learning what is the cost function, what is the loss function, and how do you actually train neural network. So till this part, it is all theory, and it is meant to give you a basic understanding and intuition of how neural networks work. Then we'll be moving on to our coding exercise, which is the iris dataset. So in this exercise, we will be classifying different types of flowers using their properties by building a deep neural network. Finally, we'll move on to the remarks, which is the end of the workshop, and I'll provide you with some more resources if you want to learn more about neural networks and machine learning in general. All right. So when it comes to machine learning, there are basically three different arenas which we can take a look at, or three different paradigms. Firstly is supervised learning, then we have unsupervised learning, and then we have reinforcement learning. So when it comes to supervised learning, neural networks is one form of supervised learning. So if you are aware, linear regression is also a form of supervised learning. So what happens in supervised learning is we use some kind of training data which is labeled. So we have the data in which we have like thousands of examples in which you have the actual properties itself as well as the label. For example, you can build a machine learning system which helps you to identify. You can feed in a picture of a car or a motorbike or any road picture, and it can help you identify whether the object in the car is a bus or a car or a motorcycle or whatever kind of vehicle it is. So to do that, you need a data set of pictures of different types of cars, buses, and motorbikes, and then you need a label of each of them. So you need to tell the computer that, okay, this is a car, this is a motorbike, and this is a bus. So that is all about supervised learning, is using labeled data to try to build a machine learning algorithm to predict that similar data. When we come to unsupervised learning, then we have two examples here. First is k-means clustering and second is anomaly detection. There are several more, but the fundamental idea behind unsupervised learning is that you have the training examples, but you don't have the training labels. So one very simple example is, you can say, fraudulent activity detection or spam classification. So you can provide different kind of text in an email, and then you can use some properties of that to have a k-means clustering algorithm or an anomaly detection algorithm to basically identify the anomalies in the data. So you can say, okay, this email looks weird, it is an anomaly, it might be categorized as a spam email. So this is what unsupervised learning is about. And finally, we have reinforcement learning. So reinforcement learning is that you don't have any form of data whatsoever. You have a computer agent which basically explores the environment and try to learn on its own from its own experience. So so these are the three different categories, and in today's workshop we will be focusing on supervised learning. So the first slide, which is what exactly is a neural network. So it's kind of a buzzword right now and a lot of people use it, but we will take a look at what exactly it is. So to give you a basic intuition, right, you can take a look at this graph, like this short graph I built here. So this graph is about, the price of a house as well as the size of the house. So here you can see that as the size of the house increases, the price of the house increases as well. So if you ask a human, right, for any given size, what is the price of the house? So one basic idea to do that is to, try to build a model to learn this. So for example, the human will probably try to, draw a line, something like this. It will say, okay, so this is the line which basically fits the model. And for any given size, you can predict the approximate price. So for example, if I say this is the size of the house, then we can predict the estimated cost of the price. So we can say this is the price for this kind of house. Similarly, since we learned from this data, we can try to predict any further um, price of the house which is not in the data set. So for example, if I say, okay, this is the size of the house, maybe it's a 7 or 8 bedroom house, it's a villa, then we can say, okay, the price should be something close to this amount. And then we can further tune the model saying, okay, the prices of the house cannot be negative. So we'll draw a straight line here. So it's either zero or it's positive. So this is like a kind of predictive algorithm you build by yourself to predict the prices of a house based on the given data. So if you didn't have these x's, right, you didn't have these data points to refer to, then you won't know what the price of a house is based on its size. But with this case, you can predict the model for that. So this is exactly what a neural network does. So you can consider the neural network as a black box in which you have some input, for which input you can get an output. So in this case, we will have the size of the house as input, and then the black box will do some computation and it will try to calculate the estimated price of the house. Now this black box is nothing, it's basically a mathematical function, and in machine learning lingo, we call this a neuron. So the single neuron is a single function that tries to compute something to give us the output. So in this case, we have the size of the house and it will give us the price. So similarly, you will see one neuron here, but if we stack a lot of neurons together and we have many layers, then that will comprise of a neural network. So in this case, it's just one neuron, but if you stack multiple neurons together, you can build a large neural network. So let's see an example of that. So if we continue the same example, right, we want to predict the price of the house. But now you see the price of the house might not be like totally dependent on the size. It can be dependent on a lot of other things. It can be dependent on the size, it can be dependent on the number of bedrooms, it can be greatly dependent on location as well. So if the house is in Orchard, if there's a house in near NTU, then the prices will definitely differ. It can depend on the transport facilities that it has nearby. So if it's near an MRT station, then the price of the house will likely to be greater. So in this case, we can form different properties. For example, if you combine the size of the house and the number of bedrooms, then you can probably estimate the family size. So this is one attribute. If you consider location, then you can have another attribute called walkability, is that how easily is it to walk and go to nearby places. And similarly, if you categorize transport facilities, then you can say it's the ease, like how easy it is to get to different places in the near the house. So these are the different properties. And if we input these different properties, you want to estimate the price of the house based on these properties. So what the neural network does is basically you have all these. So this comprises of your X, which is the input that you give it to a neural network, and this is the Y. So the function is to basically train a neural network in a way that you give it any X for which it will predict the Y. So this is how we train the neural network as well. So we give the neural network some data. The data consists of some X and some Y. And based on those X's and Y's, it will try to learn a model. Now, the fun part about neural networks is that we only need to give it the X and the Y. All this remaining part, right? If it's one layer, if it's two layers, if it's 100 layers, we don't need to figure out anything in that. It is considered as a black box, and all the parameters, which is all the mathematical computations which are in between, it will try to figure out it by itself. So we don't need to care about this part. This is considered as a black box, and we only need to care about what data we are giving. I mean, of course, we do care about the architecture of the neural network, like how do we place these neurons, what are the hyperparameters, but we don't care is what is going on inside these layers. That is considered as a black box in a neural network. So when it comes to training a neural network, right, we need data, and we need a lot of data. So the data can range from any amount. It can be 100 examples, it can be 1,000 examples, it can even be a billion examples or more. So it all depends on the use case that you're currently facing. So that is one thing about neural networks, is that they are very data hungry. The more data you feed them, the better they perform. And that is also considered a limitation as well, because on some problems you don't have a lot of data, but then in the end you need to uh, produce data in order to make neural networks perform good. So let's consider this example. So this type of data is called structured data. Structured data can be, an Excel sheet or a database. It is basically very structured. So in this case, if we recall the real estate example, right, we have this data. Suppose this is a Excel file. It has thousands of examples. So again, so this whole part, right, this is the X, which is the features, and this is the Y, which is the output. So in this case, the neural network will use these features, such as the size of the house, number of bedrooms, location, transport facilities, and it will try to predict the price of the house. So this is a kind of structured data. The second kind of data which we have, which are also very emerging and are already in use in most production data systems, is unstructured data. So not only neural networks can process text data such as the Excel files or databases, it can also process unstructured data. So this can include, voice clips. So you have your, Alexa or Siri, they all use voice data to train their algorithms. You can have image data. So object detection algorithms work on detecting images, or autonomous vehicles work on detecting images. You can have videographic data, and you can have text data as well. So for different types of data, the neural network architecture varies significantly. So for example, for audio data or for video data or for text data, these data can be considered sequential. By sequential, I mean that, the order in which the things appear do matter in this data form. For example, the audio which comes here and the audio which comes here are different. And the location of the audio points is also different. So and that's important. And similarly, if you come to a text, right, the starting lines and the ending lines, or the way the sentences are formed by using words, so you need to have the words in a specific order, unless, I mean, only that way a sentence will make sense, right? So text data is also from sequential data. And for these kind of data, right, we use a neural network called RNNs, or recurrent neural networks. At this point, you don't need to know what those are, but that is just for, an extra knowledge. Similarly, for images, right, the most common form of neural network architecture is CNN, or convolution neural networks. Again, you don't need to know what that is at this point, but that is something which is good to know. So basically, these are the two different kinds of data which we have for neural networks, and the neural networks perform well on both of them. So let's go to the first primary and the most important idea in neural networks. And this slide is really, really important. So if you have any doubt, please do raise your hand, or type your query in the chat. Okay, so let's take the example of the one neuron neural network which we showed earlier. So you can take you can revisit any example, right? So we can revisit the spam classifier. So you suppose X1 is the text of the email and X2 is the sender's ID. Based on these two quantities, these are called as features. So we have two features, but we can have n number of features in a neural network. Based on these input features, we need to predict an output. So this is like the basic architecture of a single neuron. The lines which you see here, these are called connections. So you can call them connections, or you can call them weights, or you can call them training parameters, you can call them anything. So these two lines are called connections. So every connection is associated with a weight. So um, if we have two features, we have two weights as well, W1 and W2 for each of the feature. And then finally, we have the output. So to basically, compute a value, predict something, the first thing we do is we multiply both of them. So we take a weighted sum. For example, if there are two features, then we will do x1 into y1 into w1, sorry, and x2 into w2. So here we took the weighted sum of these, and as you can see here, these are the two terms, w1 and w2, and we multiplied them and we took a sum of them. Now, if there are n number of terms, then we will do the same for n number. So we'll have w1 x1 till w1 xn. So this is the basic idea. And then finally, we add a bias term. So this is a term which is used to, it is used for efficient training. It is used for some concepts that I'll explain later. But basically, it helps the neural network to learn faster, and it helps to make better predictions. So at the second line, this is just one convenient way of writing what I wrote earlier. So this is basically the vectorized representation. So basically, we combine all the x's. We take the transform, the transpose of it, and we then multiply it with the matrix of the weights. So if you don't understand this term here, it is totally fine. It is the equivalent of the term which I wrote at the top. And then again, we add the bias here. So this is step one. Step two is, once we have computed the z value, right, which is the weighted sum of this, we have another function which are called activation functions, which I'll get to in a moment. So once we have computed the z value, we put it in the activation function, and when we put it in the activation function, we will have our final output, which is y. So y is the final output which we have here. So these are the two primary steps which we use in forward propagation, and this is the main fundamental idea behind neural networks. So just to recap once again, we take the weighted sum, which is called as z, and we put the z in another function which is known as activation function. And once we have that activation function, we have the final output. So for some more information, right, x1 and x2 are the inputs that we provide. Y is the prediction that the algorithm makes, and W1 and W2. These two are known as weights, and these are known as trainable parameters. So these are the parameters which which the neural network is supposed to learn. So the trainable parameters are W, which are the weights, as well as the B, which is the bias term. So you see this equation for one neuron, but so if you have n number of neurons, then this equation will be valid for n number of all the different neurons. So this is like the basic idea behind neural networks. So so let me tell you a bit more about the activation function. So if we consider the spam classification again, right? After having all the inputs, we need an output. So a spam classifier, right? We need to have an output, say 1 or 0. So by 1, we can indicate that it is a spam email. By 0, we can indicate that it is not a spam email. So basically, this is like one use of the activation function is to squash the input into a way which is recognizable and which we can use it to detect to make predictions. Okay, so let's talk a bit more about activation functions. So there are a lot of activation functions out there, but I'm going to refer to two activation functions which are very popular and which you will likely use in the future as well if you try to build your own neural networks. So the first one is called sigmoid activation function. So the sigmoid activation function, the graph looks something like this. So you can see the range of the function is between 1 and 0. So whatever value you give to the activation function, it will reduce it. It will reduce the value, and the value will be between 0 and 1. So this is very useful when you want to classify something. For example, in spam classification, right? Uh, if it's 1, then it's a spam email. If it's 0, it's not a spam email. So we can use the output of Z here, and G of Z will return a value between 0 and 1. For example, if it returns 0.6, so that means it is close to 1. So it is a spam email. It is a spam email. And similarly, if it returns a value, say 0.1, then it is not a spam email. And we can take this as the turning point. So anything greater than 0.5 can be considered as spam. Anything less than 0.5 is considered as a not spam. So this is like one useful function which is used to squash values between 0 and 1. Okay, so the second activation function, which is also very, very popular, is called ReLU. So the ReLU activation function, it's just a max of 0 and the Z value which you provide. So for example, if the Z value is 100, then G of Z is also 100. If it's minus 10, then we take the max of 0 and minus 10 and we get 0. So you can see this from the graph as well. Anything which is above 0, right? It is that same number itself. So if we have 5, then G of Z is also 5. But anything which is a negative number, say minus 1, right? Then it will be 0. So ReLU function is very useful and it's used in a lot of different neural networks. And there are a couple of reasons why it is used. Firstly, you can see that it is easy to compute as compared to sigmoid activation, right? You have this equation and the neural network will try to compute this value every time when it is training. But with this example, you can see that this is very, very easy to compute. This is one benefit of using ReLU. Another benefit is that there is a problem in neural networks called vanishing gradient. So I won't go too in depth about vanishing gradient, but the fundamental idea is that when you have a very deep neural network, right, what sigmoid will do that it will try to squash everything between 0 and 1. And if the neural network is very, very deep, right, uh, at some point the values will become too small to be computed. So if you try squeezing everything between 0 and 1 again and again for thousands of layers or hundreds of layers or hundreds of neurons, then in that case it becomes really, the values become too small to be computed. So that is a problem called as vanishing gradient, and then this ReLU function helps us to resolve that. All right. So there's a question in the chat. Is the screen visible to everyone? Can someone type in the chat if it's visible to everyone?
I think yes.
All right, cool. Thanks.
Wait. Okay.
All right. Okay. So why do we need to use activation functions, right? So if we go to the previous slide, why don't we stop at z? Why do we need this equation? So there are a lot of reasons why we need that, and I'll cover some of it. So the first reason is, try to turn unbounded output to a bounded output. So if we go back to forward propagation, right? Suppose this is not a spam classifier, this is a housing example. X1 is the square feet size of the house, and X2 is the number of bedrooms. If the square feet is say 100 or 200, and X2 is the size is the number of bedrooms, say 10 or 5 or 6, then if there are a lot of features, right, when you try to compute this value, it is a weighted sum. And you can imagine if there are a lot of values, then this will get bigger and bigger in most cases. So we need some way to squash the values, and otherwise the values will go into millions or billions. If we have 100 different types of inputs, then in that case, if you try to do a weighted sum, then the total will be very, very big. So that is one reason why we need activation functions. And the second, which is more important, is to introduce non-linearity. So let me give you an example, right? So in the last example, when we first tried to, build a prediction model, we drew a straight line here. So this is a very simplistic scenario. But what if the prices of the house goes exponential as we increase the size? What if it's not a straight line? What if it is something like this? What if the size of the houses increases exponentially? Or what if the sizes of, or what if the price of the house flatten as we increase the size of the house? What if we say if it's a 10-bedroom house, right? The price will be similar and it will flatten down at some point. So you see that there is a need to have non-linear curves to fit very, very complex data. And complex data is everywhere, right? You can't rely on having straight lines everywhere. You need to have some flexibility. So this is another reason why we use activation function, is to introduce some form of non-linearity into the neural network. So I'll give you another quick example. So let me share my screen again. All right. So there is a website called playground.tensorflow.org. At this point, you don't need to worry about what TensorFlow is, but it is basically a library by Google to build neural networks. So in this example, this is not an example of housing prices. But in this example, you can see this is what the data looks like. So if you consider, for example, you can consider this as a spam classifier. The blue ones are the one which are, normal emails, and the orange ones are spam emails. So when you have this kind of data, right, there is no way on earth that you can use a linear model to fit. You need a lot of curves to fit this model. So let me try to, hit the play button and try to fit the model and pause it right now. So for example, if this is so just ignore what everything's happening right now. Just try to focus on this image. So you see how we have fitted the model is that we have used all these curved lines to try to fit one kind of emails in this cluster and another kind of emails in this cluster. So this kind of fitting is not possible if you only have straight lines. So you need to have curves to fit the data properly. So this is a very important reason as to why we need activation functions. All right. So go back to the slides. Okay. So let's talk about deep neural networks. So till now we were only talking about a single neuron, but this is like what most neural networks look like. So we have a bunch of neurons in each layer, and we have different kind of layers. So in this simple example, right, you can consider this as X. So this is our input features. This can be from a real estate example. This can be the price of the house. This can be the number of bedrooms. This can be the size. This can be, the location. So this is called as input layer. We have the output layer, which is Y. In this case, we want to predict the price of the house. So this output layer is the price. And we have three layers in between. Now these three layers are called as hidden layers, and we don't really care what is happening inside them. We just need to decide an architecture, and the neural networks will take care of the rest. So some motivations behind why we need this kind of architecture. Firstly, if your data is very complex, right, you need to have several layers to make sure that the neural network it can learn these complex features. So the more complex your data gets, um, the more important it is to make sure that you have architecture good enough to basically uh, fit the data well. um, so like this is like one of the most important reasons, and another property to note is that in most cases, or usually, um, as you increase the number of layers, or as you make your neural network bigger, you will need more amount of data to train it. So for example, if you consider, or if you wake up one day and you will say, okay, I want to make 100-layer neural network, that is totally fine, and that is practical as well in some use cases. But then to make a good neural network out of that, you will need a lot of data to train the neural network, and to basically make sure that it works well. So that is another property of deep neural network, is that usually the bigger the neural network is, the more amount of data you need it to train. All right. So now we come to the training part of the neural network. So when it comes to training, right, there are a lot of things which we need to consider. And the first one is called as the loss function. So the loss function is a function which we use to tell the model, or determine how bad or how good the model is, um, working, or it is training. So one thing to note is that loss function is for every training example. So it works on each training example. And the fundamental idea behind loss function is that we give it the data and we give it the predictions. So if we refer to, the real estate example in which we want to predict the prices of the house, then we will give it the data. So for example, we will give it the real cost of the house. For example, the real cost of the house is $16,000. I mean, this is not a real cost in any way, but for this example, let's consider it's $16,000. And our neural network predicts that the cost is $18,000. So we see that there's a difference between what our neural network predicted and what was the actual value. So we need some kind of black box to tell us how good or how bad our neural network is performing. So in this case, our loss function will take in both the predictions as well as the actual value. It will do some computation and it will give us a value. So it will give us a loss, and we want to make sure that we minimize this loss. So by minimizing, I mean in this specific example, we want to make sure that after training the neural network, right, the difference between the actual value and the predicted value should be as low as possible. Only in that case, a neural network will be very accurate. So here we see a loss function, and the loss function, what it will do is it will try to compute these two values in a way to give us a loss which we want to minimize. So, so since it works on the actual data and the predictions, it is for each training example. So if we have 1,000 records, then we will go one by one and we will try to see what are the predictions and what is the actual value, and we will try to compute the loss for each of the training example. So there are a lot of loss functions which are commonly used, but one of the simplest and one of the very common loss functions out there is called squared error. So squared error loss function is actually quite simple. What it basically does is that it will take the target, it will take the predictions. So again, the prediction is $18,000, for example, or and the target is say $17,000, $16,000. So this is a prediction, this is our target. What it will do is it will subtract the prediction and the target, and it will do a square of it. So when you do a subtraction, you'll basically get the difference. That is very straightforward. So if you do 18 minus 17, you get $1,000, which is the difference between the predicted value and the actual value. But we also square it just to compensate for any negative values. For example, if the prediction was 17,000 and the target was 18,000, then we will get a negative of 1,000. So the negative 1,000 will actually mess up our calculations a lot because we need to add these losses. So just to be on a safe side, we will square all the terms which we have such that all the values, all the losses that we get are basically positive. So yeah, so it will take the y, which is the predicted, and the actual y, which is the targeted. So here is another example. So suppose the price of the house is $16,000, and a neural network predicts that the price is $17,000. Then it will basically do a subtraction between both of them, 17,000 and 16,000. It will do a square of them, and then we'll have our final loss. So squared error is, one loss function that is used, but there are a lot of loss functions out there. So We have mean squared error, which is the squared error loss function we discussed right now. We have a loss function called binary cross entropy, which is used for classification neural networks. For example, if you're building a neural network, right, you want to classify between 0 and 1. If you want to build a class, a spam classifier, 1 is a spam email and 0 is not, then you will use a binary cross entropy loss function. So another one is categorical cross entropy, which is used for categories. So if you have three categories, 0, 1, 2, then you'll use categorical cross entropy. Um, you have sparse categorical, and you have a lot of loss functions basically. And this is like one of the most common and one of the most simple loss functions which we have and which we use. So moving on. So now we go to the cost function. So the cost function is nothing. It's basically we sum up all the losses. So we remember that the loss function is for every training example. For for one example, we compute the loss. We move on to the next example. For example, in the next example, the price of the house is 20,000 and our predicted price is 22,000. So that is the loss for the next training example. So if there are 1,000 training examples, then we compute the loss for each of them. Once we compute the loss of each of them, we basically add them up together. And once we add them, we divide them by by basically do an average. So we divide them by the number of training examples which we have, and we use two here. It's basically an optimizer. So if you want to learn more, there's an algorithm called backpropagation, and basically this two, it simplifies some computation when we are doing the backpropagation. So you don't need to worry about this too much. But basically, we sum up all the losses and we divide it by the total number of training examples so that we can get an average loss. Like, so to give you an intuition, like on average, how good or how bad your neural network is performing. So on average, how much is the difference between the predicted value and the targeted value? And again, our aim is to minimize this. So we get a cost. So the cost is basically a sum over all the training examples, and we want to minimize this cost. So if the cost is very, very high, that means the losses are very, very high. When the losses are high, that means the difference between the target values and the prediction values is very high. If the cost is low, that means the losses are low. If the losses are low, that means the difference between the target value and the predicted value is low. It's not very high. So, so the next question is, how do we do that? We have the cost, right? But how do we minimize it? So there are a lot of algorithms out there which are used to minimize the cost. One such famous algorithm is called gradient descent. So how gradient descent works is I'm not going to explain it in too much depth, but just to give you a basic intuition, right? On this axis you have the cost, and on this axis you have the W. So W is basically the weights, and if you remember, weights are the trainable parameters. These are the parameters which the neural network changes such that the cost is minimum. So we need to find weights such that the difference between the target and the prediction is lowest. So, for example, uh, at any given point, right, when you start training the new network, the cost is somewhat high. It's somewhat here. We want to make sure that the cost is minimum. So, from this, we want to make sure that the cost is the minimum value, which is this one. So, we want to find some weights such that the cost is minimum. Now, to find the global minimum, it's actually not very feasible to do that, but we want to train a neural networks in a way in which we get closer to this minimum, like somewhere here or somewhere here. This is also fine. but you want to get as close as to the minimum as possible. To do that, we have an algorithm called gradient descent. Gradient descent uses a parameter called as a learning rate. So the learning rate is a parameter. It can be, it's usually a very small value, say 0.001 or 0.0001. And what it does, it tries to minimize the cost. So just to give you a very brief idea, right? If the learning rate is small, then through gradient descent, we slowly and gradually minimize our cost until we reach the global minimum or near to the global minimum. If our learning rate is too low, then we will move very slowly and we will not be able to reach the global minimum. The neural network will take a lot of time to train and it will not reach the minimum. If the learning rate is too high, if I say the learning rate is 10, then it will take too much of a big step. It might go here, it might go here after every iteration. It might go here. It may keep bouncing back here and here and here. It may never reach this optimum position. So for gradient descent, we need a learning rate which is optimal and which slowly, gradually, and in a good pace, um, basically, uh, it basically tries to reach the minimum cost. So if we have the minimum cost, that means our neural network is performing really well. The losses are very low. The difference between what our neural network is predicting and what the neural network's target is actually very low. So gradient descent is one such algorithm. We have a lot of others in the market. So we have Adam. It is another famous, um, learning algorithm. We have AdaGrad, we have RMS prop, we have stochastic gradient descent, mini batch gradient descent. So there are a lot of them. So this is like just one example and one famous way to try to reduce the cost. So now we have learned a lot of theory and now we want to actually see how do you take the data. It may be structured or unstructured. It may be an Excel file, a database, a set of images, videos, audio, and how do you actually train a neural network. All right, so this is a big picture and this slide is also really important. So suppose you have built a neural network. You have decided the number of neurons, you have decided the number of layers you want in the neural network, and you have built this network. So this is kind of a black box for you now after you have built it. So you will provide it with the input, which is X. So if we take the real estate example, right, X will be the size of the house, number of bedrooms, the location, etc. It will pass through the neural network and the neural network will make a prediction. So if the neural, for example, we take the first training example in our data set to predict the price of the house. We say it's a 6 bedroom house with 1,000 square feet. It is located near Orchard. Once we do that, the neural network predicts the price of the house. It's suppose it says it's $20,000. Not a realistic price, but just an example. Once we do that, then the neural network checks what is the actual price of the house. So it checks the Excel file. It says the actual price of the house is not 20, it's actually 25. So now we know that the actual price is 25 and a neural network predicted 20,000. Now we have the loss function. So what the loss function, suppose we have the loss function at squared error, which we learned just now. So what the loss function will do it will try to predict a loss. So it will subtract both of them. 25 minus 20, it will give us 5. 5 squared is 25. It will give us 25. Now this procedure is called as forward propagation. So now we know what the loss is. So we know the difference between our prediction and the actual thing is 25. Now through back propagation, so so just ignore what the word back propagation is. What exactly we are trying to do is through this back propagation algorithm, right? We are trying to compute new parameters. So you remember in our neural network, we have trainable parameters, a set of weights. We have W1, W2 till Wn. Plus we have the biases as well. So biases are any other another important terms. We have the W's, we have the biases. Then after doing a prediction, right, we want to change these values. We want to change the weights and the biases in such a way that the difference between these two values is minimized. So again, once we pass a input, right, we know how good or how bad the prediction is. We use any loss function to try to determine how good or how bad it is. Once we do that, we try to update the weights and the biases in such a way that the prediction is better. Suppose we update it once. Now our neural network says that no, the price is not 20, it's actually 22. In this case, now the loss will be lower. We again compute new parameters, we update these values. Now our neural network says it's not 22, it's 24.5. So you see, slowly and gradually, we try to update these weights and biases in such a way that we reach closer to the label. So the way to do that is using back propagation. So through back propagation, we try to update these values. So I hope this is clear for everyone. If there is some doubt, you can raise your hand or you can, paste your question in the chat. All right. So if no questions, then we move on. So let's again consider this example, which is a real estate example. So in this case, we have a database, a data set, an Excel file. It can be anything. So here we are dealing with structured data. So in this case, the x's are these values. These are the x's, and we have the prices, which are the y's. So these are the labels, and these are the features. So we input the features and we try to predict the prices. And the remaining part, it will figure it out by itself. So just to summarize what I just mentioned in the slide before that, is that how do we train models? All right. So initially, when you have not trained your model, right, it's a common practice to initialize all the weights and the biases randomly. So they can be any number 0 0.1, 1.2, 0.7, it can be anything. So we initialize them randomly. So this is like one way of doing it. You do have other types of initializations as well. You initialize them, you can initialize every value by 0, but that that is trouble because then our neural network doesn't learn. There are another common initializations as well. So one such initialization is called Xavier's initialization. It is commonly used in TensorFlow, but for this part, just to keep things simple, you can consider that all the weights and all the biases these are initialized randomly. All right. Then what happens is each entry in the data set, which is each training example, is ran through the model through a process of forward propagation. And then these weights and biases are updated through the process of back propagation. Okay, so once we do the forward propagation, we have a loss function which indicates the goodness of the estimate of the neural networks. So the loss function basically estimates how good or how bad we are actually performing. Once we have the loss function, we do the back prop and we try to change the weights and the biases such that the loss is low. Now, another characteristic of neural network is that once we have the data, right, we run through the data several times through the neural network to make sure that it learns. So we run through the same data set again and again and again. And the number of times which we run through is called as epochs. So if I say, or if someone says to you that I'm training my model for 20 epochs, that means you're running through your training set 20 times. And then we have an independent test set which we use to evaluate the performance of the model. So for example, in this case, right, suppose you have 1,000 examples, right? Then you will use only for it. So it can be a split, but for this case, you can say we can split it between 900 and 100. So what I'm trying to say is that the neural network will use these 900 examples to train the model. Basically, the neural network will see these 900 examples. It will learn from this data. The other 100 examples, the neural network will not see it at all. Because the neural network will not see it, we will use it after we have trained the neural network to predict on these 100 examples. So firstly, we learn from these 900 examples, then we use these 100 examples as training. So for example, you train a neural network, you're very happy with it, then you try to predict 100 examples in the test data. So just a hypothetical example, right? If out of 100, if it is able to make 90 predictions correctly and 10% and 10 predictions incorrectly, so that means your model is 90% accurate. So in rough terms, you can safely assume that if out of 100, 90 predictions are correct, it is according to what our data says, then the accuracy of the neural network is 90%. That is just one way of measuring accuracy. Of course, there are a lot of ways. We have F score, we have other ways as well. But this is like just one way you can measure accuracy of your neural network. All right. So just before the we move on to the coding exercises, right? I just want to run you through how a deep neural network works. So to give you a basic intuition, right? If you have this kind of neural network, then mathematically, first you will compute a z value for the first layer. Once you have the z value, then you will put the activation function and you will compute the y. So we use activation function and we have y for this layer. Then we use this y in this layer. So we use this y as an input to this layer. So then again we compute z value, and instead of x1 and x2s and x3s, right, we were previously doing weighted sum. So we were doing w1 into x1, w2 into x2. This time we will be doing the weights here and the values in these blocks instead of x's. Then again from z we compute the a value, which is that we put an activation function in it, then we do it again for this layer, and we do it again for this layer. So this is like the basic idea of how neural networks work. Uh, this type of neural network, which is most common, is called a fully connected neural network or a dense neural network. Why do we call that? Because you see that every input feature is connected to every neuron, and every neuron in the next layer is connected to every neuron in the next layer, and every neuron in the next layer is connected to every neuron in the next layer, and so on and so forth. So every neuron is connected to every neuron in the next layer, and this is a very common architecture, and we call it as fully connected neural networks. So when we have the input here, and finally we get the output here. It can be, a regression problem in terms of housing prices. It can be real values. It can be a spam classifier. It can be a binary value 0 or 1. It can be a categorical value 0, 1, 2, 3, 4. So this is like the basic mathematical intuition behind it. So the next thing which you do, which is the most fun part of it, is the coding exercise. So you can go to this link and you can download the files for this workshop. I will quickly paste this link in the chat as well, so everyone can see. Um, So I posted the link in the chat. I will show how to open the files, but for now you can go to that. You can go to this page and uh, yeah, you can download the files which are there. So I'll give you like 2-3 minutes to go to this GitHub repository and download the files. All right, I hope everyone is able to download the files. If there's any problem, you can uh, ask me now, or you can put it in the chat as well. That should be fine. All right, so okay then, so we'll move on. All right, so for this coding exercise, right, it's actually very interesting. So we will build a neural network that will predict a flower category. So we have three different kind of flowers. We have Iris virginica, Iris versicolor, and Iris setosa. These flowers have different attributes. For example, their petal length, their sepal length. So these flowers have different attributes. Based on these attributes, we want to teach the machine that given these attributes, you need to tell us what kind of flower it is. So this is a very famous data set, and we will use and we will build a small neural network to basically predict which kind of flower it is. All right, so this is what the iris flower dataset looks like. So here we have four attributes or four features. We have we have the sepal length, the sepal width, the petal length, and the petal width. So these are the four features of this of the flower, and based on these four features, we have a species. So based on these four features, we know what kind of flower it is. It's versicolor setosa, and um, it's virginica. So basically, you have a database or an Excel file you can consider, and you have these values. So you have the sepal length and the sepal width of these different kind of flowers, and uh, based on these, you want to predict, what kind of flower it is. So this is like the general idea which you want to do. We want, based on these four attributes, we want the algorithm to tell us what kind of flower it is. So this is the categorization, which is why. All right. So I'll open my Chrome browser and I'll share my screen again. All right. I hope you're able to download this file. Everyone is able to download this repository. So we will be working on this Jupyter notebook. This is called code.ipnYB, PYNB. So if you know how to open these kind of Jupyter notebooks, that is good. So you can use your own local machine. You can run your Jupyter notebook and open this file. But remember that this code requires a neural network library called TensorFlow, and it requires TensorFlow 2.0 version. So if you have installed that version in your system, then you can go ahead and open this notebook in your local machine. If you don't have that, then no worries. We will be using a Google uh, platform called Google Colab. So you can use Google Colab to basically run these Jupyter notebooks if you don't want to do it in your local machines. So you can quickly go to your screen. You can search for Google Colab and you can open this page. Once you do it, um, sorry, yeah, you go to the upload section. So this is the last tab of the Google Colab website, and then you can click on choose a file, and you can download this repository, and you can choose this code.ipnyb file to open this. So once you click on choose a file and you open this notebook, you will get this page. So basically, we will open the same notebook in a Google collaboratory environment. So this is all the Jupyter notebook, but it's on the cloud, and and all the computing resources are used by Google basically. So I'll give you 3 minutes to quickly download this and open the Jupyter notebooks either in your local machine or using Google Colab. So I think it would be good if you can. I mean, you can definitely watch this, but if you can do it along by yourself also, then it would be great, because in this we won't be actually coding anything. We will be running all the code. It's already done for you, but our basic intention is to understand the code and understand what is going on inside the code and how do you actually build a neural network. So I'll give you like 3 minutes to um, get this notebook set up. If you have any questions, if you have any problems, feel free to put it in the chat, or um, yeah, say it in the unmute yourself and say it. All right. Okay, I hope everyone is set up. If you have any problems, you can put it in the chat, or if you if you want to follow along using this video only, that is also perfectly fine. All right. So remember, we want to classify the types of flowers, what type of flower it is. So we have a deep learning or neural network framework known as Keras. Um, Keras is a very popular framework. We have other frameworks as well. We have PyTorch, which is also immensely popular. So with TensorFlow is also a deep learning library. Keras is also a deep learning library, but now from TensorFlow 2 onwards, just to give you some background, Keras is integrated into TensorFlow. So Keras is basically, you can consider as a high level deep learning library, whereas TensorFlow is a very lower level library. So uh, you can tweak a lot of changes in TensorFlow. You can't do it in Keras, but for most cases, Keras is more than sufficient. All right, so let's try to build a neural network. So I have an image here. So this is what our neural network architecture will look like. Of course, you can change it. You can try to experiment it with in your own way, but this is the architecture which I have chosen. So you see, you have the input layer. These are the four layers. So these are the four neurons. So these basically are the four input features: petal length, petal width, and sepal length and sepal width. We have a hidden layer of 10 neurons. So this is the black box which we have. And then we finally have the output layer. Now the output layer is not one neuron, but three neurons, because we have three different kind of flowers. And we basically want to predict which kind of flower it is. So whichever of these three neurons light up, you can say, we can see that that is the type of flower which we have. So you can again see that it is a fully connected neural network. That means every neuron is connected to every other neuron. So going back to the code, um, you can ignore the syntax for now, but just to give you a brief idea, right? In Keras, a dense layer, right? So every line is considered as a layer in the neural network, and dense is an abbreviation for a fully connected neural network. So as seen in the figure, right, we have the first layer as a dense layer with 10 units. So here the input shape is 4. That means we have 4 features, and the activation function we are going to use is ReLU. The second layer which we have is another dense layer of 8 units. So I'm sorry, I think there should be another um, layer in between. So let me just change it quickly. All right. So yeah, this is what a neural network looks like. So we have 10 layers here. We have 8 layers here, 8 neurons here, I'm sorry, and the output layer. So I'm sorry, this is the final diagram of the neural network. So here you can see the first layer, we have 10 units. The input shape is 4. That means we have 4 features. The second layer is of 8 units. Again, the activation is ReLU. And the third layer is of 3 units. Now, the activation for this is softmax. So we don't need to go very in depth about softmax, but what it basically does is that it will ensure that the sum of the outputs of all three of these neurons is between 0 and 1. What it means is that it will give us a probability. So it will ensure that, for example, it say this is 0.4, this is 0.5, and this is 0.1. So if this is 0.5, which is the highest, right? So we will say that whatever this neuron is associated with, say it is associated with iris setosa, then this is with 50% probability we can say that the flower is iris setosa. With 10% probability we can say that it is iris virginica. So the softmax will basically give us a probability for all three of them, and we'll make sure that it is between 0 and 1. So we can pick the max and identify what kind of flower it is. So yeah, this is the basic architecture of the neural network. Two dense layers of 10 units and 8 units, and then finally a dense layer of 3 units, which is the output. So if you have any queries, I'll just pause for a moment and look in the chat. If you have anything, you can post it there, or you can unmute yourself to ask. Okay, cool. So we have encapsulated the model in a function called iris classifier, and we just return the model in the end. So this is we are basically initializing the model. So you can say this is a variable, and we are calling this method that returns us the model, which is the 3-layered model. Then we compile the model. So while compiling the model, there are 3 things which you need to choose. Firstly, the optimizer. So we talked about gradient descent, which is used to minimize the cost. Another optimizer, which is really helpful, is Adam. It is really good and it is really common to use. So, so in this case, we are going to go with Adam. Then we are going to go with the loss. So in our slides, we discussed mean squared error, but here we are, since the data is categorical, we have 3 different kind of flowers, and we need to have a loss such that it indicates better in terms of categories. So we are going to use the loss called as categorical cross entropy. Of course there are other kind of losses, and the math behind this loss, or other losses, you can google it and learn and how do these losses work as compared to gradient descent. And then finally we have the metrics. So here it's very simple. We're going to simply go with the accuracy is how many examples it is able to predict successfully and how many examples it fails to predict. We are going to do that using this metric called accuracy. And then finally we have the summary. So when we type this function, we can basically call the summary of the whole model. So let me try to run these cells. I'll run the first cell, second cell, and the third cell. So you see there are no errors. We have the model iris classifier, and this is the summary. We have the first fully connected layer uh, with output shape 10, second layer output shape 8, and the third layer output shape 3. So you see the parameters 50, 88, 27. So these parameters are called trainable parameters. You sum them up, it's total 165 parameters, and all of them are trainable. So these parameters consist of the weights and the biases. So we go back to this image. For every connection, you have a weight, say W1, W2, W3 till W1. And you have a bias as well, B1, B2, B3 till Bn for each of the connection. So we have 165 nodes or 165 connections. So we have 165 training parameters. So this is the architecture of the neural network. Now we'll go through the data. So we will use this library called as skitlearn, and the data set is inbuilt in the library. So we can simply run this cell to get to know what the data is like. So here you can see in the attribute. So we have 150 training examples. We have 50 in each category. So we have 3 kind of flowers, and we have 50 examples for each kind of flower. And then we have the number of attributes, which is 4, sepal length width and petal length width. And then we have the classes, which is iris, setosa, versicolor, or virginica. Then in the code, we assign the X and the Y. So we say that the data which we have, the attributes, these are the X's, and the Y is the target. So the target is basically the class uh, of these three. So it will be one of the three classes. All right, so this is some more things about the data. You can try to read it if you want. So now let's go to an example and see what the data looks like. So here I'm printing just randomly five initial examples, and then I'm also printing the five initial targets or initial labels for these. So you can see that the example data you have 5.1, 3.5, 1.4, 0.2. This is the first training example. And this basically means the sepal length width and the petal length width. And the label for this is 0. So by 0, it means that it is iris setosa. So the first five training examples, you have the attributes and you have the labels. So all of them are iris setosa. All right. So this is what the data looks like. These are five examples, and we have a total of 150 examples in our data set. Now we will do some data pre-processing. So, both these steps, right? Data, when it comes to data exploration, seeing what the data looks like and doing the data pre-processing, it looks like an easy task because for this, this data set, the data set is already very structured and it's very organized in a way that it is easy to do data pre-processing. But when you will eventually learn more about neural networks and machine learning, you will see that this is a whole domain. So data pre-processing, data mining, data gathering, and making use of data in a good and informative way is a skill and art. It's very difficult, and it is one of the most important parts of building a machine learning model. It, in some cases, even more than the neural network architecture itself. So these two parts, they might sound a bit boring or a bit easy, but these are like really important. All right. So once we have explored the data, let's do the data pre-processing. So we are using the same library skitlearn to do the data pre-processing. So what we are trying to do is firstly, we are using a one hot encoding. So, and we pass the one hot encoding into the labels. So what we're trying to do is that um, if it's the label is 0, right, that then we don't know exactly what kind of flower it is for the neural network. So we want to make the data one hot encoded, which you'll see what it means in the moment. And the second is called standard scalar. So standard scalar, what it is used to do is to standardize the data. So for example, if you see the first five training examples, right, you have these different numbers. So we want to compress these numbers such that they have a mean and a variance of 0 and 1. So remember, we are not altering the data, as in the data that is represents, right? It will not change. It will only that it will sort of normalize the data in a way that the mean is 0 and the variance is 1 of this data. So at this point, you don't need to worry much about it. But the basic idea is that this two lines will help the neural network to train faster and converge faster. So in your free time, you can try to remove these lines and see how the neural network works. So we'll do this. And then finally, we will do a train test split. So what we want to do is, as I explained in the slides, right, we want to divide the training data into two parts. Like first is the training data and the second is the testing data. So for example, in this case, I'm using a test size of 0.2, that means 20%. So what I am doing is I'm reserving 20% of the data as test, which the neural network will not see, and the remaining 80% of the data will be used in the training. So the proportion in which you split the training and the test data, it's I mean, it depends on your use case actually. So if you, for just, I mean, it is not applicable to all the use cases, but for example, if you have say a million training examples, then the test size can be as low as 5% or 1%, and the remaining 95 or 99% of the data you can use it for training. But here in this case, I'm going for 20% test size and the remaining in the training set. So this is another variable called random state. So random state, what it is doing, it is trying to randomize and shuffle the data around, because you see in this example, it is very organized. For example, all the first five examples are iris setosa. So all the 51st examples are also iris setosa. So we want to shuffle the data in a way such that a new networks doesn't overfit and it learns a bit faster and a bit in a better way. So we are using this function called train test split. It is part of this library, and we are trying to split the data between the features, the attributes, and the labels. So X train is X train and Y train. These are the training data and the training labels. And similarly, X test and Y test are the testing data and the testing labels. All right, so let's run this as well. Now, this is the final step, which is training the model itself. So so this is the name of our model, which we initialized earlier, iris classify model, and we'll use a dot fit function to train the model. We will give it the X train and the Y train. So remember, we won't give the model the testing data. We'll only give the model the training data. Uh, we will run it for 200 epochs, and we will give it a batch size of 5. So, I mean, for the sake of time, right, I won't go into too much depth into what batch size is, but basically, we are going to give the model 5 training examples before it performs back propagation. So, instead of doing back propagation after every training example, we will wait till 5 training examples and then update our weights and the biases. So we'll click on play and we'll train the model. So here you can see it's training very fast. Like if you have a big use case, it might take days, even weeks to train a model, and it might take GPUs and a lot of RAM. But in this case, it's a very small model, so we can train very quickly. All right. Okay, so here you can see in the first epoch, right, the accuracy is only 36% because the weights are initialized randomly and the neural network doesn't know anything at all about the data. So after a first run through of the data, we get a 36% accuracy, which is very, very low. It's very poor. But as we run through the data again and again, and we do backprop and we, change our weights and biases, the accuracy slowly increases. So in the next epoch is 53%, 57%, 62%. And if you go to the bottom, it's actually really high. So after running through the data 200 times, the accuracy is 98.55%, which is really good. You can see on epoch 24, epoch 198, the accuracy is 99.5%, but after running through data again, it drops a bit, but that is fine. So for this example, you can see the accuracy is really good. And similarly, you can see the loss as well. So the loss was also um, very high in the beginning, but as we move along, it slowly decreases. All right, so once we have trained the model, so by training the model, it means that we have finally found the best weights and the best biases, such that the loss is minimum and the accuracy is highest. So once we have trained the model, we can evaluate it. So we are using the test data and the test labels to evaluate, and then we're printing the test loss and the test accuracy. All right, so it says the accuracy is 93%, So you see that there's a difference between the training accuracy and the testing accuracy. Such differences, I mean, if it's not too much, then it's fine. That means your model is able to generalize well in the data set. And you can see it performs with accuracy of 93% on the test data. So you see the final loss is 0.08. You don't need to worry too much about this at this point. And the final test accuracy is 93%. So you can safely assume that our model accuracy is at least 93%, if not 98% in some cases. All right. So now we finally try to run it and we try to infer from it. So in this case, right, I will try to feed it some of the testing examples, and I will try to determine what kind of flower it is. So I gave it, some training examples, like all the testing examples I had, and I will try to predict from the model which we just trained. So we see the, so okay, so here we print the prediction as well as the final value. So here what it means. This is the output of the softmax function. So I mean not the softmax function, but this is the output of the final neurons. So here we will pick the highest one, which is this one, and we will categorize it as one. So you can see that if we pick this one, which is the highest one, and we pick the actual value. So if the actual is 1 here, that means it is iris setosa, and our neural network says with maximum probability then that this is the maximum probability, the first one. So here you can see that this and this corresponds. Well, that means our prediction and the actual value is correct. Similarly, if you go to the third example, you can see that the neural network predicts with the maximum confidence that the third value is the actual flower. So, and in the actual set, we see that the third is one. So, for example, if this is iris setosa, then we can see that it is able to predict this correctly as well. So what we did is we basically fed in some test data. So instead of this test, right, you can have your own petal length, petal breadth, sepal length, sepal breadth, and based on these, it will try to predict what kind of flower it is, and you can actually check that it works fine. So in the inference, we can see that it is working well, and whatever training testing data we give, it corresponds to the actual values. So here we see the model is working fine. So this is our coding exercise. You can try to play around with it. You can try to change the model architecture. You can try to change the number of epochs, the batch size. You can try to do some more data pre-processing. Um, you can basically play around with this notebook and try to see if you can increase the accuracy, and you can. So you can increase the accuracy a lot, at least 95% and above. So you can play around with the data and see how you can do it. So this is one example of how we built a small neural network, which started with giving it all the flower attributes, and it will predict the kind of flower that is there. So this is all about the coding exercise. So let me go to my slides again. All right. So just to give you some closing remarks, right? So neural networks, as we understood, is a way of doing machine learning in which the machine learns to do a task by learning from data. That is the training examples. In this workshop, we use text, but it can be images, audio clips, anything that you like. It is a very vast topic, and we just covered like the very, very basics of it. So we have barely skimmed through the surface, and there are a lot of fundamental topics that you need to understand to actually learn the new, like how new networks work and how they actually perform and how do you optimize them. Another point is that neural networks is a relatively mature field. I mean, there is a lot of research going on, but a lot of research has already been done. It is not something like reinforcement learning, which is pretty new. And a lot of commercial systems that are out there that claim that they use machine learning, right? They use some form of neural nets. So your autonomous cars, object detection, facial detection, sentiment analysis, classification. A lot of these things are already using neural networks in production. A lot of enterprises, a lot of startups, a lot of companies are using neural networks to automate their tasks, and it's a really mature field if you talk strictly in terms of machine learning. So if you're really keen to learn more, I highly recommend you start with the Coursera course. So Coursera has a deep learning specialization, uh, which it's taught by a Stanford professor called Andrew Ng. You might have heard of him. It's Andrew Ang. He's very famous, and the specialization is really good. So if you want to, actually understand and go in depth of how neural networks work, then you can definitely go to the specialization and try to learn from it. If you want to keep track and you want to stay on top of deep learning research, these are some conferences which you can take a look out for. So some of the important conferences are, um, NeurIPS is really important. It's really cool. ICRR is also really cool, and all these workshops are also, all these really conferences are also really, prestigious. So all the latest research, the best, the latest, and the greatest, you can say. The first point where they are introduced is usually in these conferences. So NeurIPS, ICLR, ICCV, ICRA, you can be on a lookout and try to see the research papers that are published on these topics on in these conferences to stay on top of it. Apart from that, we have some other resources as well. So firstly, I mentioned the deep learning specialization, which you can take a look at. There is a TensorFlow developer professional certificate, so it's also by Coursera. So uh, deep learning specialization basically covers the mathematical aspect and the working of neural networks, whereas TensorFlow developer certification focuses on how to actually code the neural network. So how do you make them work and how do you actually code them? So this specialization focuses on that. You can take the Stanford CS230 course. It is there on YouTube for free. So it is also taught by Andrew Young, and you can. It's a really cool course, and it follows in tandem to the deep learning specialization. So he basically teaches the concepts which he teaches in deep learning specialization as well as some advanced concepts. So this is also a really cool course. If you want to learn more, then you can refer to this book called Deep Learning. So it's also written by a very famous author. He's currently the head of special projects in Apple. So if you want to, understand more about deep learning, you can also refer to this book. So yeah, with that said, we have come to the end of the workshop. Thanks a lot, everyone who stayed till the end to learn all the concepts. I hope the workshop was good for you. I hope you understood all the things, and also now you have a better interest and a better understanding of neural networks. Uh, if you want to learn more about it, then you're more motivated to do so. And yeah, that is basically about the end. So if you have any questions, you can unmute yourself, ask right now. You can put it in the chat. You can email me later as well. My email is there in the GitHub repository. Yeah, so that is all for now. So I'll stop the recording, and yeah, I'll be here for a couple of minutes if you want.